slightly more difficult to understand is the bending of light when it goes into a material. It turns out that that comes from the fact that the light moves somewhat slower inside the glass than it does in the air. As a result, it bends towards the normal. You could imagine this if we had a surface with grass here and pavement up on the top. Then if I took a little two-wheeled system that's going in this direction, when the slower side hits the grass, or excuse me, when the leading side hits the grass, it's going to slow down, and this other side will turn. As a result, the whole thing is going to turn and move onto the grass at a much steeper angle. So let's draw an original one. Like that. So you see we have a bending of the motion. The same thing happens for light. We can also see this by matching the wave fronts as they come into the glass. Now we characterize this speed of light by something known as the index of refraction. So here we have several different media, and we have their index of refraction. The idea behind an index of refraction, n, is simply the speed of light in a vacuum, c, divided by the speed of light in the medium. So the larger the value of n, the slower the speed of light within that medium. As you can see here, for a vacuum it's exactly 1. For air it's very nearly 1. But as we get to other things like, for example, glass or sodium chloride, those are about 1.5. So light travels only about 2 times 10 to the 8th meters per second in glass or salt. In some other materials, it may be much slower. The heaviest glasses, 1.89. Some have much less indices of refraction. Water, only 1.33. The most that's known is diamond, 2.42. And then the rule for describing the relationship between the angle of incidence and the angle of refraction is known as Snell's law, and it says that the index of refraction in the new medium times the sine of theta in the new medium equals the index of refraction in the old medium times the sine of theta in the old medium. n1 sine theta 1 equals n2 sine theta 2. And that, as I said, is known as Snell's law. Let's talk a bit more about refraction and Snell's law. We can rewrite it to solve for theta 2 by saying the sine of theta 2 is just n1 over n2 times the sine of theta 1. What does that tell us? Well, if n1 is equal to n2, then this is just 1. Sine of theta 2 equals the sine of theta 1, and so the two angles are equal. So that's the first key idea. If n1 is equal to n2, then theta 2 is equal to theta 1, and the refraction does not cause the light beam to bend. In general, very little would happen, and you might not even notice that you'd entered a medium. So that's what we see right here. The light beam comes in, there may be a reflection, probably not much of a reflection actually, if the two media are the same, and the refracted light just goes straight through. No change in direction whatsoever. Now how about if n2 is greater? Alright, if n2 is greater than n1, that means this n2 on the bottom is going to be bigger. This fraction will be less than 1, so the sine of theta 2 will be less than the sine of theta 1, so theta 2 is going to be less than theta 1. The angle is always measured relative to the normal, so if theta 2 is smaller, then we bend towards the normal, as is illustrated right here. Light comes in, it bends towards the normal, theta 2 is smaller than theta 1. That happens when n2 is greater than n1. Well, then the third possibility is that n2 is less than n1. In that situation, this fraction is bigger than 1, sine theta 2 is bigger than sine theta 1, and theta 2 will be bigger than theta 1. In other words, the light will bend away from the normal, and we get a larger theta 2 than theta 1. One key thing here, no matter how big n2 is, or how small n2 is, the refraction cannot bend a beam so much that the refracted ray stays on the same side. In other words, the refracted ray can at most be bent here to 90 degrees. It can't bend up here into the reflection region. This is all just reflection.